3 days ago, a geomagnetic storm struck Earth, and the planet hasn't calmed since. For 72 hours straight, streams of charged particles from the sun slammed into our magnetic field, shaking it like a vast invisible ocean. To most people, the storm ended when the auroras faded, but to scientists watching the data, the story didn't stop there. Deep above our heads, the plasmasphere, a shell of charged gas surrounding Earth, is still vibrating. Holding onto the energy it absorbed, the satellites orbiting at geostationary heights show something unusual. The electron flux remains 10 to 100 times higher than normal. It's like the planet is still humming from the impact, a low electric resonance echoing through the magnetic field. Every atom, every ion in near-Earth space is still trembling. The storm might have passed, but Earth is still charged. The plasmasphere is Earth's living shell, a sea of charged particles held in place by invisible magnetic lines. It breathes with the sun. Every flare, every gust of solar wind stirs it, charging and discharging the space around our planet like a pulse, high above the equator, at about 5.6 Earth radii. The GEOS satellites have been recording something extraordinary. The electron flux, the stream of high-energy particles, has risen from 10 to the second to nearly 10 to the fourth, a hundredfold increase. That means the near-Earth environment is still supercharged, its radiation belts swollen with excess energy. Scientists call this the energetic flux, the constant movement of charged matter that connects the sun, the Earth, and everything in between. When it rises too fast, the planet's magnetic field vibrates, auroras bloom, and satellites feel the strain. Every atom above us is still trembling, and space, it seems, refuses to rest. According to new modelling from the UK Met Office, the sun has launched not one, but 3 separate waves of plasma into space. The first shock front has already begun its long journey across the solar wind, a faint ripple moving through the void. The second follows close behind, carrying a denser pocket of charged particles, weaving through the interplanetary magnetic field. And then comes the third, the strongest, the most concentrated, expected to sweep past Earth between October 7th and 9th. From above the solar system, it would look like 3 glowing rings expanding outward from the sun, each one pulsing through the darkness. On the top-down solar density maps, you can trace their paths, 3 waves converging on one small blue world. Scientists call this an impact window, but for the rest of us, it's a watch window, a moment to look up, to listen, and to wonder what might follow. 3 waves, 1 planet, all arriving under a full moon. When the full moon crosses Earth's magnetotail, it drifts through a river of charged plasma flowing behind our planet. In that region, space isn't empty. It's alive with slow-moving ions and electrons torn from the solar wind and trapped by Earth's magnetic field. As the moon moves through it, something remarkable happens. Its sunlit side builds up a positive electric charge, while its dark side gathers a negative one. The result is a powerful electric gradient stretching across the lunar surface, a natural capacitor drifting through space. At the same time, its alignment with the Earth and Sun amplifies both gravity and reflected light, focusing subtle forces across the magnetosphere. That's why, during every full moon, our magnetic field seems to stir auroras, shimmer differently. Plasma currents twist a little more. It's not superstition, it's electromagnetism in motion. Every time the moon glows at its brightest, Earth's field stirs. As Earth's magnetic field vibrated, the ground itself began to answer. In the span of just 4 days, A chain of powerful earthquakes rippled across the Pacific Ring of Fire. On September 30th, a magnitude 6.9 quake struck the Philippines. A day later, a magnitude 6.0 shook the island of Bali, Indonesia. On October 2nd, a 6.1 tremor hit off the coast of Kamchatka near the same fault zone that produced last month's 8.8 megaquake. And on October 3rd, Japan felt a 6.0 quake near the same trench that once unleashed the Great Tohoku disaster of 2011. On the USGS world map, the pattern is clear: 4 red circles, aligned like notes on a fault line melody. It's not proof of causation, but nature rarely moves without rhythm. March 11th, 2011, the sea rose, and Japan shook with a magnitude 9.1 earthquake. It was one of the most powerful quakes ever recorded, a wall of water racing toward the coast faster than a jetliner. Entire towns disappeared beneath the waves. The ocean carried ships inland, turned harbors into chaos, and left behind silence that lasted for years. Seismologists often remind us each step up in magnitude means 32 times more energy released. 2 magnitude 8.8 earthquakes release the same energy as 1 magnitude 9. That's the scale we're dealing with. A world of forces far beyond anything human hands can restrain. Some scientists believe that the energy once released doesn't simply vanish, it redistributes, moves along the faults, waiting for the next break. Energy doesn't vanish, it waits. While Earth trembled, the sun was far from quiet. In the last 36 hours, solar observatories captured a series of eruptions unlike anything seen in months. The AIA cameras, imaging at 171 and 304 angstroms, revealed what scientists call a canyon of fire. Massive arcs of plasma rose from the surface, curling like ribbons of molten light before breaking free into space. Each eruption sent filaments of plasma, light, and matter intertwined, cascading outward in every direction. For a brief moment, the solar corona shimmered like a storm of gold dust, the surface alive with movement and heat. Most of the material was ejected northward, missing Earth's direct orbit. But the outer edge, the sweeping flank, is still expected to brush our magnetic field. When it does, it will deliver the third and strongest wave, the one we're all waiting for. To understand what's coming, we have to look at the numbers, the heartbeat of space weather. The KP index measures how much Earth's magnetic field is being disturbed by solar activity. It runs from 0 to 9, calm to extreme, and on September 30th, it hit 7, a G3 storm. Since then, the field has been slowly recovering. But the next waves are already on the way. Forecasts show a new rise between October 7th and 9th, the same window when those 3 waves are expected to arrive. This period is what scientists call a geomagnetic window, a moment when the Earth is most exposed to solar energy. There's another factor at play, the Russell-McPherron Effect. Around the equinox, Earth's 23.5-degree tilt allows the solar wind to connect more efficiently with our magnetic field, drawing more energy in. Imagine it like this: our planet leans just enough for the solar wind to bite deeper into the magnetic shield. For observers, here's what to watch. Time October 7th to 9th. BZ less than or equal to negative 10 nanotesla for 2 hours or more. KP6 or higher, and auroras could be visible below 50 degrees latitude. If the numbers align, the sky will too. If you want to see the sky respond, step outside between midnight and dawn. Look north, or simply look up. The aurora will compete with the full moon's light, so it may appear faint, a ghostly arc across the horizon. If you have a camera, set a high ISO and expose for 15 seconds, enough time for the hidden green to emerge. You might capture the glow of a magnetic storm, or just the silence that follows. Either way, it's worth looking up. Some people feel these storms without ever seeing the lights. They speak of headaches, pressure in the chest, restless nights. Scientists believe it's not imagination. Geomagnetic fluctuations can subtly shift our body's rhythms. Changes in the ionosphere alter the electric balance that guides our hormones, including melatonin, the chemical that tells us when to sleep. For a planet made of charged matter, it's no surprise that we, too, respond to the sun. We are, after all, made of charged particles too. In every storm, there's a frequency we can't hear, but somehow, we still feel. While the sun burns and storms ripple through our skies, another traveler drifts silently past Mars. 3I Atlas, a fragment from another star system, older than our sun, faster than any comet we know. NASA's deep space monitors confirm its trajectory, but no new images have yet appeared on the agency's FTP servers. Astronomers are waiting for the next dataset, a spectral reading that could reveal why its glow has turned a vivid green. They expect traces of cyanogen and diatomic carbon molecules that breathe green when struck by sunlight. Older than the sun, faster than any comet we know, and growing brighter still. When the images arrive, we'll decode the light. Maybe it's just plasma and gravity. Or maybe it's a reminder that we're still learning how to listen. In the quiet between solar storms and interstellar travelers, there's a story still unfolding, one written in particles, light, and time. The sound fades, replaced by a single radio echo, the faint wow signal from long ago. On screen, a line appears: 3I Atlas, between science and silence. Subscribe and stay on. Watch, the next wave is already forming.